So if we kind of think about where we left last time, right? I thought it might be just worthwhile just kind of building the stepping stones from we started talking about these A's and B's and C's and a type constructor that's parameterized by some type A, which we don't know what A is, and even though that we didn't really cover much territory, like there was kind of a lot of new concepts that we had to start thinking about, and it might be worthwhile just like going back and kind of building to this point from a simpler type, like say like bit, for example. And so if we think about, we ended with defining this optional A, and then we went and defined map optional. It takes a function A to B. So let's just put the the brake on a little bit and just kind of step back and kind of get to this point a little bit. So let's go back to the simple times where things were a lot easier. There was no these A's and B's and C's, and we're just talking about ints and bools and chars and all those concrete things. So let's just think of like a very simple type called small num, which is 1, 2, 3, 4, or 5. So we can think of it like a subset of integers. So this is a sum type in the sense that it's 1 or 2 or 3 or 4. So cannot pass. Okay, yeah, fair enough. Right, the one we've got to change these to be the spelling because Haskell thinks 5 is a special thing, not just the thing we want it to be. So let's say small num, right? So you say small num is, if I say there is a value constructor called 1, which is when I call it with no arguments, I get back small 1, is how I would think about this. 2. But think about I've always got to have anything of type small num is either 1 or 2 or 3 or 4 or 5. It can't be 1, 2, 3, 4, 5, 6. That's where we're going to use product types. So if we jump back in, we can think of like some point in two-dimensional space is going to be, I'll say make point 2D, is going to be two small nums, the x. You can think of this as the x and the y in our coordinates. Okay, that's great. And now if we jump back into here, actually I'll just shock in deriving show. I'll do that for here. So now if I say point 2D, this could be 1 and 1. No, I meant make point 2D. Thanks Haskell. And we say it's make point 2D is 1 and 1. And I could say 1 and 2. So we kind of have seen this before. This is kind of sum types and product types. But if we think about the kind of relationship here, is that when I've got some function, and let's say like add takes a small num, or let's say add 1 takes a small num and returns a small num. What that's really saying, like this type says that I have to take something of small 1, of type small 1, and I have to return something of type small 1. So if we think about, well, can I say add 1 of hello, right? And here you can see that if you try to do this, and I'm just going to equal undefine, if we tried to call add 1 of hello, it would say couldn't matrix vector type small num with actual type char array, a list of char, which is a string. That makes sense because we said, no, you've got to give me a small num. But what are the values for small num? And the values for small num are 1 or 2 or 3 or 4 or 5. So that's how the type checker will make sure that you have to call me with something of type small num. Right? So nothing is there, but it's quite important. If we quickly implement this, we could say if it's 1, then you give me 2. If it's 2, I'll give you 3. If it's 4, I'll give you 5. And if it's 5, we'll pretend like overflow, we'll wrap around and give you 1. right? So add 1 to 1 gives me 2. Cool, that works. But I could just return, can I return hello here? Well, no, right? Because hello is not of type small num. I mean, we can see what all the types are for small num. So that's fine. But if we think about it, there are only 5 values for small num, which is different. And I'll probably just remove that whole bit. Yeah, so what I kind of want to say here is that if we have a small num that's only 5 values, whereas there's actually more values for the product type, 0.2D, right? Because we can have with small num, right? We've got our 5 values there. But with 0.2D, we can say, you know, if you said, well, what are the values of that are of type 0.2D? And it turns out the values would be 1 and 1 and 1. You know, we can this if we kind of step back and we think, well, the values are all the ways we can construct something of type 0.2D. And when it comes to constructing, we look at the value constructors, and there's only one value constructor. So the only way we can construct something of 0.2D is to call the make 0.2D constructor. And then what can we give it? Well, it needs to take 2 small nums, and we actually can see this. If we ask for what the type of make 0.2D, it says, well, I'm just a function, and I take 2 small nums, and I give you back something of type 0.2D. So, you know, 1 isn't a value of, even if we said 1, 1, that's not of type 0.2D. We've got to use it to construct, we've got to pass it to the constructor. So make 0.2D 1, 1 is a value of type 0.2D, and that's a type of value 2D, and that's a type of value 2D, and we can kind of keep doing this until we would say like 5, 5. So we can see there's 5 different values that we could pass for the first argument, and there's 5 different values we could pass for the second argument. So so there are in total 25 values of the type 0.2D, right? And that's kind of, you know, that's kind of the power of product types. So if we kind of look here, we'll see that if we didn't do this, we couldn't use product types and we can only use sum types. If we wanted to encode the fact that there are 25 points in this, you know, two-dimensional plane of just 5 across and 5 up, we'd have to say something like make 0.2D 1, 1 or make 0.2D 1, 2. And we have to kind of do this, you know, and then this you make 0.2D 5, 5. So, you know, the product types is kind of like almost like a shorthand. It's an easy way to express the fact that, okay, yes, there are 25 values of this type 0.2D, but like I don't have to spell them all out. So I can just say, well, it's small num takes a small num and a small num, right? And that's going to construct the value. Cool. So if we think about that, all right, that's fine, makes sense, and kind of gives you an intuition for the fact that, you know, it's kind of straightforward. Small num, you look at the definition, you see all the values. For 0.2D, you don't see all the values there, but then you can think, well, it's all the different combinations of small num that are going to be all the values constructed with, you know, this value constructor. So let's, you know, so kind of using the fact that we can use product types to kind of let us have a bunch of different values without having to like spell them all out, let's define something called box. And all box is going to be is it's just going to make a box of type int. Now again, we saw here that, you know, when we said 0.2D, small num, that was equivalent to saying make all the values, and we make 0.2D 1, 1, 1, 2, or we said it's equivalent to, you know, having a sum type that was 1, 1, and then Well, make box int's kind of the same thing, right? instead of having to say, make box 1, make box 2, make box 3, I can just say, you know what? It's just, I'm going to have a value constructor which takes an integer and then constructs something of make box. So you can see here that we got every value that int can take on, right? All the values of int are also going to be, the number of values there are for int is going to be the same as the number of values there are for type box, right? Because we're just wrapping around the integer. So now I need to jump back up into here. Oh, where? Oh, no, it's fine. So we saw, at kind of the end of the first session, that it's quite handy to be able to map some function over a list of integers. And so if we have the list 1, 2, 3, we can see that we can map +1 over each element in the list. And in this case, we'd we'd call +1 on 1, +1 on 2, +1 on 3, and get back to list 2, 3, 4. And so it'd be kind of handy if we could have the same thing for our box. I want to say make box of 5, and I want that to return back a make box of 6. And of course it says, hang on, what the hell is this map box thing? So let's define that. So whenever we have to define a function, the first thing we have to do is think about, hey, what's the type? What are we dealing with here? What can I take in? What can I give out? Right? That's kind of the point here of a function, is to say, hey, I don't take in everything, although I might, but I'm going to constrain, what are my options? So mapping a box takes a function. So what's the type of a function? Well, we've seen a type of a function because we're defining a function right now. But the type of a function, will look like something like this. It will take, in the case of say an add function, it takes an int, it takes 2 ints, and returns an int. So in our case, if it's mapping over a box of integer, or if it's mapping over our data type box, well, box can only have an integer, right, associated with it. So we can't take a function that, any arbitrary function. We can only take functions which take an integer and return integer, right? So we have to say we'll take a function that, given an integer, will return an integer. And we can't say, well, it's anything and returns integer, because we've only got a box of integer. So it has to take an integer. Or you can't say, it takes a char and returns an integer, because we don't have a char to give it. We've only got an integer that we can give it. Likewise, it can't return a char or a string or anything else, right? Or a double, because we need to wrap it back up using the make box constructor, which takes something of type integer. So that's no good. So we've got to take a function that, given an integer, returns an integer. And we need to take a box. And then last, we need to return a box. And so you can think, okay, map box, easy. I'll take some function, f, which is going to be of type int2int, and I'll take some box b, and I'll just return box of 10. And that's fine. So if it's not map box, but it certainly will type check, right? Because the type checker says you have to return something of type box. And so it looks here and it says, is box 10 of type box? Well, it is. Oh, sorry. Make box 10 of type box, and yeah, it is, because we can say, if we think about, if we say make box of 10, and what's the type of that? It says box, because box has one value constructor. I gave it an int, I get a box. If you look at the type of make box, it says, give me an int, I'll give you a box. So we're on. So you think that's easy. So now it's like, all right, well, let's try it. Let's say map. Let's go back to our example. Map box +1 over 5. Oh, killer. We didn't. The old deriving sure hurt us. And it says, cool. We call map box +1 over the box of 5, and it says 10. Okay, that's strange. So it didn't. Now, Of course it didn't work because we hard coded mapbox of 10. But the thing here is it type checked. So it type checked, but it's not correct. And that's a really important thing, right? Just because it type checks, there's a difference between a program that type checks and a program that's correct, in the sense that you can't encode easily the idea of that this thing maps over this structure. As long as the types match up, and in this case it did. It said, well, you've just got to return something of type box, and we did. Make box 10 is a value of type box, but it's not the thing we want it to do. So what you actually want it to do is say, well, instead of 10, I want to call whatever's inside B. Right? I want to pull out the value outside of this box, right? And I want to apply it to this function. So how do you pull out the integer out of the box? We use pattern matching. We can say, well, there's only one way that something of type box was constructed, and that was through the makeBox value constructor. And then we'll say, well, we'll give the name x to whatever the integer was that was passed to makeBox. And what we'll do is we'll call the function f on x, which will return an integer, which we can say here, and then we'll wrap that back up into makeBox. And so now, if we call +1 over the box, we see 5 and we see makeBox is 6. So it's doing what we expected, yet both times they type checked. And that's because, if we think about it, so let's have a little think, and it's basically, there are a lot of functions of this type, box to box, right? Because, box is, we just saw that make box of 0, make box of 1. So, for every, I could not implement like this. I could say, actually, make box of 0, for whatever reason, is 10. And make box of 1 is -20. And anything else, just call f of x. And this is, got to handle the -20. So in Haskell, you've actually got to apply the minus. So now you'd be like, okay, cool. That looks good. Then if I say 0, it says 10, and if I say 1, it's -20. So you actually can, you can see there's a lot of different ways you can implement this, of something of this type, but this is the idea, right? Haskell first will try and match this if it's 0. If it's 1, it'll try and match this, and also try and match this. But the point here is that we've got this box here that that kind of holds to an int, that contains an int. But then I go to you, I go, hey, integrate. We all love ints, great for measuring things, but it'd be really good if you could do strings. Could you give me a box of strings? So then you're like, well, I don't really want to say string box. I don't want a different type. I still want a box. But now I want to construct it. I want strings. So you might be tempted to say, well, what if I just say make box of string? Now the problem here is that each value constructor must have a unique name. So we can't have the same name, but we could say make box int and make box string. And int takes an int, string takes a string. Now if we come back to here, we're like, well, int, that's not good for a string. So we're going to have to create another thing called mapbox, where you take a string to string. And what I mean by this is that, give me a box, because you might want to say something like, I want to map the function, and here we're going to use a lambda expression. So we're just going to say, takes some argument, it's a function that takes a single argument n, and here we'll say string, right? Sure. And it's going to append the string appended to it, right? And then we're going to apply that over a box of hello. And it won't be a box of hello, it'll be a make box string of hello. So this is something that we could do. We want to do something like this, and we want that to return make box string of hello appended. That's what we want when we call this. But the problem is we need a whole new function because we've said that this function has to be int to int. So we can't. Sorry, it's a little call there. We can't reuse this map box because we've said specifically here this only takes ints to ints. So we have to define another function where the function you pass is string to string. So if we think about, well, all right, how would we, I'm going to remove this, how do we implement this? Well, it's the same thing, right? Take the f, which is a function of type string to string, but this time we're going to have to, we can't use, we've got to think, well, if this value was constructed with make box int, don't do anything. So in this case, we're only interested if you constructed a box using the make box string constructor. And we'll get that value string. And then we'll wrap that back up in a make box string. And we'll call f to the string. And that will give us a new string, and then you beauty. But in the case that you constructed something with an integer, n, we don't want to do anything, right? We just want to like wrap it back up, like, oh, we can't do anything here, so we'll just kind of give you back what you gave us. And so that means likewise over here, we can't just say make box anymore because the constructor has changed to make box int. There is no value constructor of make box. There's only make box int and make box string. So we say make box int and we get our, say our n here, and we wrap that, we call make box int with the f applied to the value n. But it's kind of like the opposite here. If we get a string, when you call make box int string, we kind of just want to wrap it back up. We don't want to touch it because we can't touch it. Now the compiler, if we run this, compiler says duplicate type signatures, right? Because you've got to have unique names. So this one we have to say, oh, okay, we'll call this make box int. Make box int. This one's make box string. And all good. So now we can kind of go back to our example, and we had, so now instead of make box, it's make box int. So there's going to be a box that contains an int, namely 5, and we're going to map 1 over it. So again, we can't just say map box because there is no function called map box. It's map box int or map box string. So we return something. We return the value make box int of 6, or make box int 6, right? But if we try to call map box int on map box string of hello, and we're going to call our function, this lambda here, which just says, cool, I take a string and I return the string. This is appended with the string appended. It will say, hang on, I couldn't match type int with this list of char, which is type string. So we have to call, and that's because we have to call our map box string. And here we go. We get the value make box string with hello appended. So this works, but you can see the problem, right? Great today, but then tomorrow I'm like, yeah, so ints and strings, really good, really liking both of them, but how about doubles? We'd love to see some doubles. And so you're like, oh, okay, well, I guess I can come back here and I can say, well, if it's make box double, and I'll use double, and then I've got to have a map box, double, and you can kind of say that you're going to get this explosion of, types or values and functions because we've got to implement a concrete function for each type. What we really want to say is, I actually don't care what's in the box, right? I just want a box of something, but I don't want to care about what's actually in the box. And this is why we love parameterizing our type constructors. What you really want to say is, I want to introduce a variable. I want to introduce an argument A, right, a parameter A rather, to our type constructor box, right? So now I don't want box to be a concrete type. I want to be able to say box of int and box of string and box of double and box of char, right? They're concrete types. Now I just want to say I know how to construct concrete types, but I'm not a type myself, right? I'm gonna be like a higher order type. I'm gonna like, give me your favorite type. You want a string? Give me whatever you love, and I'll construct a type that's box of that type. So now we can just go back to make box, right? And we can say make box A. So what that's saying is, well, what I can do is I can use the fact that if I pass int to the type constructor box, then that means I'll create a type box int, right? So box is not a type, but now if I pass int to box, this is a type. And I could say box string. And I could even say box of string. It doesn't matter. You just pass me your type and I'll create a type of box it. So this, this is weird, but you can think of A here, equals box of string. You don't care. That's the whole point of A. A is to be like, it's arbitrary. I don't care what it is. It's just that you give me it, I'll give you back a type. I'll construct a type of box of A. So how does this help us then only define map box once? Well, we can go back to what we originally wanted was we just want, right, a box. We just want one implementation of map box. So if we kind of start with what we had for the integer case, we get that f out. We immediately see a problem. Well, actually, let's just pattern match on box on the second argument and pull the x out. Now, if I said what's the type of x? Well, before I think I did something like this where I said x was A. Now, that makes it look like these two things are the same thing, but this could be anything, right? The idea here is that x is of type whatever A is. It's of type A, and A will depend on whatever the type is at the time you're calling it. So we just say, let's just get the value out of the box. And we apply f of x. And then we wrap that back up, and voila, back to how we had it before. But we've got a function here that's int to int, right? And we've got a box, and we said box is not a type. There is no type box. There's box int, box bool, box char. So you might say, well, okay, I can solve that problem. I can just say box of int, and then a box of int, and then int to int. So that's fine. And if we compile that, it says, I don't like it. Why doesn't it like it? It says, I don't know what the hell. Okay, cool. So let's just comment out these. But it's quite interesting if you compare these two, right? That mapBoxInt took a function and a box and returned a box. But now at the type level, there is nothing called box. So to have a type, to get a type, we need to call box, the type constructor box, with some type. So in this case, A is integer. And that type checks. That says, cool, yeah, box of int, that's a type. And there are things, what are things of that type? Well, box of 0. Rather, make box of 0, and make box of 1, and make box of, that number. They're all values of type box of int. Cool. So we're good. We're going, and we're getting somewhere, albeit very slowly. So let's compile that. Beautiful. So now we go back to kind of, the good old days where we could say, map box plus 1 and make box of 1. Awesome. Make box of 2. You map plus 1 over the value inside. But what if we say hello, make box of hello? We know we can do it. We can say make box hello. Right, that's fine, because in this case, if we ask what's the type here, it says it's a list of char, which is a string. Or we could say make box of true, which in that case is a box of bool. But if we try and call plus 1, it says, hang on, the first argument here is a function takes an int to an int. You told us that. You told us, if you look at the type of make box, it says it takes a function int to int, and it takes a box of int and returns a box of int, but you've just given me a box of list of char, right? So it kind of feels like, how do we solve that problem? Like back to where we started, right? Like, maybe we have to just, we have to just say, damn it, all right, this is an int, and we're going to have one for string, and we're going to call this max box string, and then a box of string and a box of string. And then we do the same thing, we grab it, x, and we package it back up. Now, funny part here is that if you look, the implementation of mapbox int and mapbox string are exactly the same thing, but the types are different. And now if we call, if we go back to our example here, instead of mapbox itself, we have to call string, and now we can pass in this lambda string, and we can append v2, and we see we get what we wanted, but so now we've solved the problem of we don't need to have a separate constructor, value constructor for each type that we want to support, but we still have to implement a function for each type, even though the implementation is exactly the same. And this, at last, is why we talk about, we love these arbitrary types, we love these generic types. What we really want to say is, if you look at in each implementation between string and int, never did we care about what the value of x was, right? There was no assumption. We didn't use anything to assume that x was a certain type. X could have been Boolean or string or int. We didn't care. We just said, look, we just pass it straight to f. F knows how to deal with something of whatever this type is, of type A. And so what we can do is we can say, well, instead of having to have a separate function for each type, we can use the fact, right? We can use the fact that we can use this A here to say, actually, we don't actually care what's in the box, because we don't. At this point, it's a box of A. We don't care. So what we can say is we can replace int with A, and we're going to replace the return type with A. And we can, instead of saying constructing, instead of the type box int, we can say box A. And we can do that for both the box we're going to map over and the return box. So now we've kind of generalized this. We've said, actually, you just give us a box of A. We don't care what box of A is. So give us a function that takes an A to an A, right? So this says that whatever A is, we don't care what it is, but whatever it is, you've got to return the same thing, the same type, right? So if A is of type string, then you better hope you return something of type string. But this just means that I could put anything in here. And, it would still work conceptually. The type checker will be happy with it as long as these A's are the same, right? So alrighty, QuickTime is not wanting a bar of more than 30 minutes. Maybe there's something to that. So, okay, where were we? So we're talking about box of A. Yeah, so, again, you might say like, well, where do these A's come from, right? Where are they defined? Every time we've used, in this case of the A, well, we introduced the A as an argument to the type constructor of box, such that the value constructors could then use it. But here we've just kind of like pulled A out of the air. Where the hell is A coming from? And in the type system, if you just introduce some arbitrary letter, right, what you're saying there, what you're indicating to the type system is you do not care what the type is. You can almost think of it like underscore. Like, I don't care what the type is. I just want to give it a name. Whatever you decide it is, give it a name, because the fact that I give it a name means that here, even though it's arbitrary, right, this could be int to int or string to string. But the A here says A to A just means that it has to be, you have to give me something of some type A and I'll return you something of type A. I can't be of different type. So while it doesn't tell you, we don't care what type it is, we do put a constraint on the fact you've got to give us, if I give you an int, you can't give me back a string. I won't be having a bar of that. You can only give me back a string. You only give me back the type that I gave you. And a box of A, it's the same idea, right? That if I take a box of A as the argument, if I take something of type box A, right? This says it's got to be of type box A. Well, what is the type of box A? Well, it depends. If you're mapping over a box of integers, or not integers, but if you're mapping over a box int, then A will be int, right? And if you give me a box int, so if I'm more specific, right? Let's drop this. Let's drop the int, because now you don't care about it. It's not specific to ints. It's general, right? It's a general implementation. And I kind of wanted to move that down here, right? So if we drop the int, because we don't talk about ints anymore, what we're really saying is if I call map box on, say, +1 on make box 10, then in this case, A equals whatever the type of, box of A. If you think about the first argument, right, this function here, +1, it's, in this case, the A to A will be int to int. That's fine. The second argument, make box 10, well, its type is box of int, right? And the return type, if you give me a box of A, we've said if you give me a box of A, you've got to return a box of A, then you better give us back a box of A, which in this case is a box of int. So I could implement this as, I could just give you back exactly what you gave me. And that would be a fine implementation of mapbox. Be weird, I could say +1 on make box of 10, and you just give me back the box. But it type checks, right? And it type checks because we just said, hey, as long as you return something that was the same type was also the same type as the thing you gave me, then we're fine. And so this is okay, but actually we can't implement with this type. If mapbox was this type, we couldn't implement mapbox because you could only do things that were of the same type. So actually you could say +1. Oh, sorry, I'll jump. This is fine. No. So we say, okay, all right, I'm going to use the function now. So I'm going to apply A to F. Or apply F to A. I think it's apply F to A. That sounds a bit nicer. But now I'm going to take this function f, which is of type A to A, and apply it, to x, which is of type A. All right, so that's important to know, that x is of type A. And so if we do that, we'll see that we have something pretty close. 11, that was good. Was it a fluke? No, it wasn't. Okay, it's pretty good. Are we done here? Like, can we, if I now say hello, and I now take our lambda, which was string, and then it adds version 2, that worked. Okay, cool. So we're using the same implementation of mapbox for now a box of string and a box of int. But what about if I took this function? If you map, just like I can say map, or rather, I can say +1 on 1, 2, 3. But what if I wanted to say convert 1, 2, 3 to be the string representation of 1, 2, 3? So I'm going to define a lambda, and I'm going to take some integer n, the number, and I'm going to say show n. And so here, show basically, you think of it, just converts it to its serializable form, to the string version, if you like, of whatever the element is. So what if we wanted to do the exact same thing? We should be able to do the exact same thing, right? For map box, we can say, well, I just want to take whatever's in box, and I want to call show on it, and now have a box of so in this case, I'll give you a box of int, I'll give you back a box of string. So I say make box of 10. What I wanted is make box of 10, or rather, but it says it couldn't find an instance. And if we think about it, it makes sense, because we said A to A. We said the type has to be the same. If it's int, it has to be int to int. If it's string, it has to be string to string. But here, we just passed it a function. We passed mapbox a function which takes an integer to a string. And that's why we need B here. Again, B seems arbitrary, because it is arbitrary. What B says, it just says, look, I'm pretty arbitrary as well. I don't tell you anything about what I really am. But I will tell you that I'm not A. I can assure you that I'm not A, I'm B. And that means that now, if that's B, I also want to be able to say, I don't return things. If you give me a box int, here I have to return a box int. But what I want to say is, if you give me a box int, I don't have to return a box int. Maybe I want to return a box of string, or a box of bool, or a box of anything else. So B just says I'm not A, and it distinguishes. So now we can see that in this case, this is the most generic version of mapping we can have, right? We can do the case where it's int to int, but we also can do the case where it's int to string, right? If A is int and B is int, then that's int to int like we had before. But now we can say if we call this show n function on the box, we'll see it works exactly as we expected. That it wraps it stringifies, if you like, the value inside. So we're finally here. We've made it. We've made it to our map box, and that's really the value here of generics. It's not that A can tell you, using A here doesn't. It's basically a placeholder for when you actually call me, I will be a value. Also, I will be a type. I'll be some type, but you don't care. That's the thing. You're saying I don't actually, I'm signaling to the type system, I don't care what the type of A is, because I never refer to it. Now that would be different if X, right, which is of type A, if I said, hey, before I call X, I'm going to add, V2 or with extra. Now it would matter, right? It would matter this wouldn't compile because not all types have this double plus operator defined. And so now you have assumed, you've assumed that X is something that has this operator defined on it. And so you can't just say A. Now you'd have to say, well, there's other ways to talk, there are ways you can say, I only want things to have this operator defined on it, but you can't be generic because you've assumed something about the type of X. So I hope that's kind of, I think, I was really trying for this to be like a half an hour, like, here's what, parametric types are. But yeah, turns out it wasn't as simple as I hoped. But I hope now that kind of helps build intuition for like why we have optional A, which is, full of A or empty, right? It's the same business. We could have said optional is full of ints or empty, but again, with optional, we don't actually care what the full of is, right? We just care that there is some A that we're going to wrap with a full, and so that's why we use this A. All right, that's me.